Okay, this is the last page we went through, and this is also the summary of previous stability analysis of infilter coupled converter. The result is this. The characteristic equation of source coupled converter or infilter coupled converter is a product of two terms equals 0. So if the uncoupled converter is initially stable, this term equals 0, does not have any RHP root, then question here is we need to investigate the presence of any RHP root here, this term equals 0. So we'll be using the Nyquist stability criterion for that purpose, and this term is defined as minor loop gain by Dr. Middlebrook. Last time, I think we discussed this. So because we are talking about the interaction between infilter and downstream converter stage, we need to review the impedance characteristic of this simple low-pass filter. So this part is defined as G1. Last class, we defined this as G1. And this one G2, right? So G1 is a series connection of this inductor and the ESR of that inductor, and asymptotic plot of G1 is this one. This is start from here and go straight with this slope. So maybe we need another asymptote showing this. Is G1. This is G1. This one, the other one is G2. G2 is also series connection of this capacitor and this ESR. So at low frequencies, you have this slope of capacitor, and at high frequencies, there is ESR 0. Okay, so G2 asymptotic curve of G2 is this. Okay, and here we defined three different impedances of this infilter. GIF infinity is input impedance of this filter, measured, defined with this output open, and this is the output impedance of this filter with input port shorted. And this is the output impedance of the filter with input port open. We don't use this, but later we will use this. And this is input impedance of downstream converter, because if downstream converter is uncoupled, then it's better to use this notation, GIU, right? So this input impedance is just connection of this asymptote and this asymptote, because we are following the larger one between several asymptotic curves, and this GO0 is this one, because this is the parallel combination, so it follows the low trajectory, smaller trajectory. So our problem is investigate the characteristic of this type of impedance overlap. This is the input impedance of this converter, GIU, and this is output impedance of this line infilter. Evaluate with this input port shorted. So we have this problem. We have seen this problem before, right? That was load coupled converter case. At that case, at that time we are considering this one. So there is a converter. You have a converter located here, and this converter is directly connected. Assume converter is directly connected without line filter to downstream converter. Then we have this situation, and this converter is powered by ideal voltage source, but this is load coupled converter. And this is source coupled converter. Source coupled converter. The problem itself is the same. Because this input impedance of this converter, source coupled converter, and input impedance of this downstream converter, they are about the same. Has the same structure and same characteristics. So here we have GIU of downstream converter, and we have GIU here. So you have two impedances here. One is GIU, and this one is GOF0. Here we have GIU, and the other impedance was GOU, output impedance of uncoupled upstream converter. So at that time, we investigate problem of this, right? So shape of this GOU is very similar to the shape of this GOF0. So we have same problem, but in this case, we have previously we had line filter. So this GIU is modified to GL. So we studied the interaction between GOU and the GIU. But here we are comparing this GOF0 and the GIU, and plot is shown here, right? So this is overlap. If they overlap, trajectory of minor loop gain goes to outside of the unit circle, and during that trajectory, if this trajectory encircles this critical point, the system becomes unstable. Okay, that is the result of previous analysis based on the Nyquist stability criteria. So here, so we need to investigate the phase characteristic of this converter. So this minor loop gain defined here is TMN. Let me write down TMN here. TMN is GOF0 divided by GIU. Okay. So previously minor loop gain was defined here. At that time, that expression was something else. Okay. But here we have this equation. So the phase of this is this. So during this overlap, you just investigate the phase characteristic of this polar plot. So, but this at low frequencies, the input impedance of this source uncoupled converter stays horizontal line at the value of minus RIC. Okay, just the RIC. So value here is 20 log Vs divided by Is, but phase is minus 180 degrees, so it has negative resistance characteristics, and so there is the phase of this GIU, and the phase of this output impedance of infilter stays 90 degrees during this frequency, and it goes to minus 90 degrees. So based on that, you can identify boundary of phase during this period, right? So phase is smaller than 270 and larger than 90 degrees. That means trajectory is this side. So at the peak point, this phase is 0. Phase is 0. Then this phase becomes minus 180. Okay? At this peak value, phase of this output impedance of infilter is 0. Then phase of this minor loop gain is minus 180. So it goes like this and it becomes unstable. All right? So this problem occurs very often. Right? So this is called infilter induced instability problem. Right? So when the overlap occurs, the overlap between two impedances occurs at low frequency. This is loop gain frequency of this converter. So below this, basically it stays this minus 180 degree phase. So if overlap occurs here, then converter must be unstable. So converter is unstable. I showed 3 examples. Okay. So for case A, there is a small gap, right? So converter is stable. Integrated converter is stable. It overlap here, but phase characteristic of this GIU is different from the minus 180 degree, but there is a good chance that the converter still remains stable even though they overlap. If overlap occurs in this region, definitely the converter becomes stable. So for these examples, I simulate and I draw the polar plot. The case A is here, and this is a B, this is a C. So trajectory of loop gain, A is this one is B, this one is C. They are all stable, right? But they are all prone to the instability. Because if something happens, then maybe this peak value will exceed this, then this becomes unstable. Suppose something happened, this frequency of this peak moves this direction, then system becomes unstable, right? So this is the minimum requirement. If this peak value of output impedance of infilter is lower than this low frequency magnitude of converters infilter, then we have stable system, but that is the minimum requirement. So to have some tolerance, to have some robustness, people use two unequal sign here. So this is the recommended condition to make sure the integrated converter is stable, right? So for the case A, there is a gap, very small gap. So it's very risky, but converter is stable. And for cases B and C, there is overlap. But the phase characteristic of this input impedance is somewhat favorable to us. Okay, so maybe safe characteristic. So converter may remain stable, but obviously it's very risky, dangerous design. So you should avoid this all the time. Okay, and another example is shown here. This is this what example of a buck converter, right? So suppose this is the output impedance of infilter located here, and this GIU is input impedance of this downstream buck converter. The operational region of range of this buck converter is here. Okay, input voltage here is 46 volt, and the current, DC current, is in the range of 4 to 8 volt. So for this case, Vs is 46 and Is is 4 amp. Then this value, 20 log Vs divided by Is, is magnitude of low frequency asymptote of impedance, is this 21.4 dB. Okay, so that is the case here. This is the case with 4 amp of this input current, right? So now this current is doubled, right? Then this value becomes smaller, okay? It drops by 6 dB because the current is doubled, right? Then this value becomes this one. Then you have problem, okay? So with this maximum increased load resistance, this low frequency asymptote of input impedance is reduced by 6 dB. It goes like this, right? Then there is overlap. This is the fatal overlap, right? Because the phase characteristic of this is minus 180, and phase at this peak point is 0. Then the phase of the polar plot is minus 180 at the frequency where this trajectory exceeds this unit circle, which is shown here, right? So this is unstable, okay? Previous it was stable. So in general, the high line and heavy load is the worst case for this stability analysis, right? So when you are designing any infilter, you should consider this worst case. Maximum in voltage. No. Minimum input voltage and maximum load current is the should be the checkpoint. Okay. So a low line heavy load condition is the worst case for the infilter induced instability. I saw many students and many engineers just making this mistake. Let me show the simulation of this scenario. So this is the previous buck converter, and this initially the load current was 4 amp, and it steps up to 8 amp and go back to the 4 amp. So initially we have gap here at this interface. Then during the step load change, this one goes down here, okay, becomes unstable and goes up, okay. Then it becomes stable again. Simulation result is shown here, right? This is the average value of this current, 4 amp, 8 amp, and this is the input voltage, okay, output voltage of this infilter or input voltage of this downstream buck converter, and this is output voltage of buck converter. So at this instant, when this current is doubled at this point, it starts oscillation, okay? And when this returns to the original value, the oscillation starts decreasing, and eventually it becomes stable, okay? So it happens, right? So they design filter without considering this problem, then they'll see this trouble a lot, okay? So the oscillation is occurring here, and frequency of oscillation can be predict the location of this overlap, okay? So maybe this is, I don't know. Assume this is somewhere between this, right? So then period of oscillation, TOS is 1 divided by 550, which is 1.8 millisecond, right? So if you take close look around this distance is very similar to 2 millisecond, right? So oscillation occurs at this frequency. If this overlap occurs at this frequency, the period of this oscillation should be much larger, okay? If the overlap occurs here, then this oscillation will be at higher frequency, right? So this provides some region of trouble, okay? By just observing the oscillation frequency, the problem will occur here. Then they attach some additional things, right, to avoid this. Okay. All right. Then let's talk about the conditions for the minimal infilter inaction. Means the condition for the stability was this one. Condition for the stability was this one. Okay. Stability requirement, but this is just the minimum requirement. Minimum requirement, and maybe this with this double inequality can be considered conservative requirement. Conservative requirement, right? Okay. How about this? Stability is okay, but still you have problem with this. Right? GOS, you have this GI prime and double prime, triple prime. Right? So you have minimal in-filter interaction, means in-filter does not affect the performance of downstream converter, not significantly. That means you should have this inequality. So GOF, GO0 should be smaller than everything for different input impedance. That is very, very demanding requirement for some case. So for the typical voltage mode control, the general shape of four impedance is like this. This is the GI double prime, and this is GI U, okay? And this is the GI prime, and the GI triple prime, GI prime, okay? Basic difference between them is these two are closed loop controlled, closed loop input impedance. To evaluate this impedance, GI double prime and the GIU, feedback loop is closed, right? So with closed loop, there is some attenuation, okay? Because of the loop, feedback loop, you have some additional attenuation or boost, okay? Because we are talking about the impedance can be boost, but this is the open loop system. So this is not controlled because this is only determined by power stage parameter because the feedback loop is opened, right? So this is the general result of just using open loop situation, okay? All right. So this is very important. These two are closed loop input impedance. Okay, and the other two, this one, they are open loop input impedance. One is just simply open loop impedance. The other one is open loop impedance with output shorting, right? So you cannot close the feedback loop. This is the definition of the open loop. This is the definition of input impedance. Measured under this condition, that is the requirement that comes from the EET, right? Then what you're going to do to improve this? You need boost this, but this loop is opened, voltage loop is opened. Then what you're going to do? Add current loop. If you use current mode control, there is just a loop, right? The feedback loop, output voltage feedback loop is cut, but still there is an internal loop due to the current mode control. Then that current mode control, somehow that boost this thing up here, right? So that is the one benefit of current mode control. Current mode control improve this open loop input impedance characteristics and mitigate the problem of this. And at that case, it's much easier to meet these four requirements. Okay. So we are discussing the voltage mode control, but it is interesting to think about why where the problem is coming from. Okay, so that is this example. You are using voltage mode control. Usually people, they don't use voltage mode control for the boost converter. They should use current mode control. But I selected this example because still you can use voltage mode control, but performance will be very poor. But it shows the problem of in-filter interaction more clearly. Okay. All right. Then conditions for the minimal in-filter interaction, but this example fails to meet the requirement. So this is a case of non-minimum in-filter interaction. In-filter interaction. All right, so okay, let me switch my glasses. Okay, so here there is a sufficient gap between this output impedance of the in-filter and this closed loop input impedances, but there is an overlap between this output impedance and open loop input impedances. So it does not meet the requirement. So we have overlap here, this much between output impedance of in-filter and this one is what? This one is GI prime. Okay? No, GI triple prime. And with GI prime, you have this much of impedance overlap. Okay, so you violate two of the required conditions, and the price of this is this loop gain characteristic to change like this. This one is the uncoupled case, and this is the source coupled case, in-filter coupled case. So there is some variation, and I think I said this previously. This variation shown here is directly related with overlap in this region, and deviation here is related with overlap in this region. This is another overlap, but we don't have enough separation here. So because of that and some phase characteristics of this, you have boost of this much in output impedances. So this is the result. Okay, but this is not that detrimental, right? Because if you have overlap with this closed loop input impedances, you have a stability problem. System is unstable. You have overlap here, but it really doesn't matter the stability of the system, but performance will be changed, altered. Okay. All right, so let's take a specific example. This is case study number 1. So I picked this boost converter with voltage mode control. This is the input condition. So I just fixed this IS, okay? But you should use the maximum value of this and minimum value of this, okay? And the output is this, the switching frequency, and this is what? This height of this external lamp feedback compensation is selected like that. And we have 4 impedances, input impedance defined previously, closed loop input impedance, and this is output nullified input impedance. To have this condition, to have output nullified condition, the loop should be closed. So this is actually closed loop input impedance. So there are 2 closed loop input impedance. Closed loop impedances, and this is the open loop, and this is also open loop, GI prime and GI triple prime. So this is the dangerous one. Okay. All right. How they look like? As shown here. This is the 4 impedances. We went through this. All right. How do I know this? I proved this. Okay. I derived these different impedances using EET. It is might be almost impossible to derive all of this analytically, but EET simplifies this. So I think I used EET several times deriving this. So this is the general shape of voltage mode controlled converter, boost converter, buck converter, they all have this common shape. This is GIU and GI double prime. Okay, they are closed loop impedances, input impedances, closed loop. Okay, and this GI triple prime and GI prime are what? They are open loop impedances. Okay, take a look at the phase. Phase here, this GIU and GI double prime has minus 180 degree phase. So this is, if you overlap in this frequency with these guys, these two guys, that is very dangerous. Okay, fatal overlap because of the phase characteristic, and these two are non-fatal. Okay. If they overlap, not this one, with this one, that the performance will be varied, but the stability still remains okay, right? I did every details about this in the reference paper, and the derivation of this is shown. All the details of derivation of these four impedances are in the textbook, right? So among them, this one is very interesting. GI double prime. Okay, if you know this, then you know this GIU because you have feedback theorem. So first you evaluate GI triple prime and the GI double prime, then use ET. Okay, then feedback theorem that will give you this one, and this one is relatively easy. This one is most complicated, GIU actually. And all of them are not that easy. So this is the prediction. So low frequency asymptote of GIU is the same as low frequency asymptote of GI double prime. The value is this. This is the input voltage, input current, and the number is 9.9 dB, somewhere here. Okay. So, and I verified all these curves using the computational method, and I measured some of them. I didn't show here. Okay, and this is the prediction. And this low frequency asymptote of GI prime is very easy. This is the ESR of inductor, and omega G prime is this frequency. Okay, this is the zero frequency of due to the L and ESR of L. This is the resonant frequency of power stage, not filter stage, power stage. And this is crossover frequency of uncoupled converter. And finally, omega G double prime is this, right? Okay. So you believe this, okay? Paper. I'll introduce the paper later. Textbook. And evaluation of this one is very interesting. Okay. So this will explain very clearly the concept of output null condition. With that, you can derive this. Without that concept, it's very difficult to derive this. Okay. And input impedance characteristic of converter. We went through this several times, many times. So this is VSIS curve of this constant power load. P is constant because efficiency is 100%. Then output is fixed, R is fixed. Then this power is fixed. Then operating point is somewhere here. So assume at this particular situation, point is located here. Then DC value is Vs and Is. Now that you increase the in voltage to this direction, So this is the Vs prime. Then you should decrease input current to have the constant power. That means this slope is negative. So it has negative incremental input resistance. That can be easily found here. Just taking the derivative of this, and result is this. RIC. Okay. This should be RIC. RIC. Right. Example of this. Verification of this. This. Okay. So this is our analysis, graphical analysis. This is the simulation result. All right. This input impedance stays on this low frequency asymptote of this point, and this is loop gain crossover frequency of frequency. Maybe this higher frequency it follows the inductive slope. Okay? But some analysis there is some variation. It goes to the two slope and come back to one slope. Right? So the Erickson, he has the book. In his book, he somehow he analyzes this, and it goes something like this. Strange, right? So it really doesn't matter. At high frequencies, it becomes inductive, but most cases, this characteristic is not important at all, right? So this is only important. Negative resistance characteristics. Okay. And I simulate 4 cases of impedance overlap. Okay. So this is the output impedance of 4 different line filters, in filters, filter A, filter B, filter C, and filter D. Right? All of them have overlap here, but overlap is occurring at this frequency, and this frequency, and this frequency. Right? This is the filter parameters I used. So all of these filters are critically damped. I select Q of 1. Right? That is the properly designed filter. Okay? With that, I played with these parameters to locate this resonant frequency at 4 different cases. But you can imagine this. This is stable. This is stable. This can be unstable. This can be unstable. If overlap occurs here, that case is definitely unstable. Right? Because this overlap is moving toward this dangerous region gradually. So I plot the polar plot of these 4 cases. This is the polar plot of case A, this line, okay, the most thin line, this one, and filter B, still okay. Filter C is encircling, passing through this critical point, so it's unstable. And filter D is definitely encircling this critical point. So AB is okay. Okay. Maybe the performance will be changed a lot, right? But still it remains stable. So this overlap is moving this direction. It starts from A to B, going this direction. Then this polar plot is rotating in counterclockwise direction, right? So if it goes further, then this will rotate, okay, to be more unstable. Okay, so stability is confirmed here, right? Then what will happen? The loop gain of this converter. They should provide the consistent information about the absolute stability, right? So one guy says it is unstable. Then the other guy should say that system is unstable either. Loop gain characteristic is shown here. So this is the case A. Okay. So some strange behavior, something. Then still A, B, they are stable because at the loop gain crossover frequency here, then phase is less negative than minus 180 degree. So they have very small phase margin, so performance will be very poor. But still, they are stable. For these two cases, C and D, okay, D, at this crossover frequency, phase drops like this. This means there is two unstable roots in the system. Okay, so system is unstable. And C is also unstable because it touches around this loop gain crossover frequency. It touches this minus 180 degree. So this is also unstable, right? Or this one. This is D is definitely unstable. C is also unstable. And A, B, they are stable, right? So this is the case of step load response. I don't know what kind of step load I introduced with some step load change. This is performance of uncoupled converter. Stable, right? But this is not good characteristics. It has this large peak, relatively large peak, some oscillatory behavior. Usually, if converter is properly designed, although transient response should show something similar to this beautiful first order system characteristics. Why this shows this oscillatory behavior? Because we used voltage mode control for the boost converter. So that is something forbidden, right? So because of that, phase margin of this converter is very small, very small. It's less than 20 degrees or something like that. So it has some oscillatory behavior from the beginning. And if you add this filter A, B, this oscillation intensifies like this. And filter C system becomes totally unstable. And with D, it becomes more unstable. So the stability is predicted from the Nyquist analysis and predicted from this loop gain analysis. Okay, that's only for the absolute stability. It has same information about whether the system is stable or not. Okay, the other, how much the system is stable, they have different meaning, different implication. Maybe you learn these things in the previous semester when we are discussing current mode control. I addressed the implication of different things, okay, to predict the stability and relativity stability of same system. Okay. So we know the stability of this system. Then let's take a look at the change in the performance. Okay, let me finish this up, right? So this is the comparison of output impedance of in filter and 4 input impedances. So we have overlap here, and this is filter parameters. And for all frequency, this occurs. So this output impedance of in filter is sufficiently low than the closed loop input impedances, but it becomes larger than open loop impedances at some frequencies, and during that overlap frequencies we have some problem. Okay, so this is expression of audio susceptibility of converter with in filter. So this can be ignored because this is what? This is closed loop impedance is much larger than this one for all frequency. So this becomes 0, can be considered 0. Then you have this thing, right? So this additional attenuation is coming from the in filter itself. Then next, this one is output impedance. This is expression for the output impedance. This one is again what? This is closed loop input impedance. So this becomes 0, considered to be 0. Then remaining is this. Then this ratio, GOF divided by GI prime, which is basically overlap, which is this one. Okay, but it appears in the numerator in second floor. It appears upstairs. So this output impedance of this uncoupled converter is boosted this much at this frequency. Okay? So you have this. This is obvious from this asymptotic analysis. And finally, this is the loop gain analysis. So this can be considered 0 because this is the closed loop input impedance. This is 0. Then this guy, this ratio, no. This one, the polar product of ratio is shown here. This area. So this small, strange looking area, which is this, appears in downstairs. Then because of that, okay. Because of that, you have dip here. What I'm trying to say is this should be the same thing, right? Same area in different shape, right? I think they're about the same, right? So it's related with this, and this one is related with this area, and this area is related with previous output impedance. This one is this one. This one is related with this, and this effect produce this change in the output impedance. Finally, I'd like to explain this. Okay, so this is the simulation result of step load response. Usually this step load response is closely related with output impedance characteristics. So whenever you see the output impedance characteristic, you should think about the transient response of your system, because that's very easy to predict and very accurate. Okay? We are not using any exact analysis, just some heuristic argument that works very well. So this is transient response of output voltage due to this current change, IL. Okay, this is the output current change, and this is load current. This is a boost converter, so they are different. Load current and inductor current is different, all right? And it has some oscillation. It has some low frequency oscillation. This is due to the what? Small phase margin. You are using voltage mode control to boost converter, which is forbidden in general. Because of that, this shows some oscillation, and this oscillation is directly related with this is the uncoupled converter output impedance, shows this peak, right? So this peak is narrow, so it has some peaking, so some oscillation will be generated, and frequency of oscillation is oscillation occurs at this frequency, then oscillation period is predicted from this equation. So oscillation period is 1 over this FC, which is this, right? So this high frequency oscillation, I don't know exact. This damped oscillation, the size is reducing, but if you measure this period, then it will be very similar to this, right? But if the infilter is coming in, then output impedance has this original peak here. It was there in uncoupled condition with infilter, maybe somehow reduced, but still there is peak. So this high frequency oscillation is similar to the previous case, but in addition to that, you have this another peaking, low frequency peaking, produce this one, okay? And the frequency of oscillation is same as this peak frequency. So that period, this oscillation period, gonna be 3.3 some millisecond. So maybe this is the correct number. Okay, I didn't check accurately. Right? So it provides very useful information about this transient behavior of converter. So this general rule applies for all the cases. Suppose you have maybe some another peak here, then there is some very fast oscillation in the beginning. So you have peak is moving this way, then this oscillation is very slow, like this. Oh, final conclusion. This is just a summary. Conservative requirement for the stability is this one. The output impedance of filter peak value should be much smaller than low frequency asymptote of input impedance of downstream converter. Maybe 10 dB, 12 dB will be good number. Okay. And requiring for the minimal in-filter interaction, not having this type of overlap is this. But it is almost impossible to meet this requirement just using just the voltage mode control. With current mode control, this is very easy to meet. But with the voltage mode control, meeting this one is very hard. Because you can just meet this, but that does not guarantee you are meeting this second, third conditions, because meeting this one. So to meet this one, this peak value should be somewhere here. Okay, this guy will meet this one, first requirement, but it fails to meet these two requirements. So for the voltage mode control, converter is prone to in-filter interaction. Okay, performance change. Okay. Right. That is one problem of voltage mode control. With current mode control can be improved, but there is another problem with current mode control. So we'll discuss that next Thursday. Okay, all right, thank you.